go right. So who have to go first? Okay. So, and shall we go first?
Okay. Share my screen. Share my screen. Okay. Can everyone see this okay? I assume so. Okay. So this week, today, I will be presenting a paper titled Can Luminous Lyman Alpha Emitters at Z 5.7 and Z 6.6 Suppress Star Formation? So the main objective of this paper was to analyze Lyman alpha emitters. Lyman alpha emitters are galaxies. These are high redshift galaxies, so very, very young galaxies. High redshift galaxies are believed to be young star-forming galaxies. They're compact, they're metal poor, they're low mass. They're considered dwarfs in some scenarios. And so the peculiar thing, or the identifying factor of these galaxies, are that they emit strong Lyman alpha emission, which is the transition from an electron transition from n equals 2 to n equals 1. And so these galaxies are important to analyze, given their high redshift and given their high emission of Lyman alpha. These galaxies are important in analyzing the history of the epoch of reionization. So they want to, the authors want to study these galaxies and the environment around these galaxies. The main thing they want to study is how these galaxies can affect star formation around neighboring galaxies. Because the theory is that if you have a high, a very luminous source of Lyman alpha, such. Oh. Can everyone still hear me? Hello, hello. Okay. Okay, cool. Sorry about that. What was I saying? Oh yes. So the main thing that the authors want to analyze is how the radiation from these Lyman alpha emitters can suppress star formation. So the theory is that these luminous Lyman alpha emission are strong enough to ionize and heat up the neutral hydrogen gas in nearby galaxies, therefore preventing cooling of hydrogen gas. And if we don't have cooling of hydrogen gas, there is not very likely that we will have star formation in surrounding galaxies. Okay, so the main analysis, the main data analysis that was conducted is that they used the Subaru Silver Rush survey to look for and find two categories of Lyman alpha emitters. They divided them into bright Lyman alpha emitters and faint Lyman alpha emitters. The main difference between the two is that they had a cutoff range for the magnitude of these different galaxies. The magnitude range was 24.75. So essentially, if you have let me see if I can find here we go. So they define bright Lyman alpha emitters if they observed a galaxy, one of these galaxies to be less than 24.7 magnitude, and a faint Lyman alpha emitter was anything up with a magnitude greater than 24.75. And these are the two narrowband filters that they use to analyze them. The NB816 is used for redshift, to find Lyman alpha emitters at redshift 5.7, and the other filter is used to find the same Lyman alpha emitters at redshift of around 6.6. So the way they do, like I said, they divide these two galaxies into bright and dim. And then what they do is they construct these annuli after finding and dividing up these galaxies into bright and dim, bright and faint. They then find the bright ones and construct annuli around the bright ones in different radii, in different size ranges. So here you can see that after they define bright and faint Lyman alpha emitters, they construct rings, annuli rings around a bright Lyman alpha between less than 1 megaparsec, between 1 and 2, 2 and 3, 2 and 3, 3 and 5, and finally a ring of size between 5 and 10 megaparsecs. And then after finding these annuli, they use these different ranges to find, okay, how many counts of faint Lyman alpha emitters can we find between this ring, between this ring, between this ring, and between this ring? And so after calculating the flux density and the count, here we go. After calculating the flux density and the count, the number density of these faint Lyman alpha emitters around a bright one, they then plot them on a figure with respect to the brightness, the luminosity of the central Lyman alpha emitter. So here we have in this figure, we can see that the brighter a Lyman alpha, the brighter the central Lyman alpha in the aperture, the brighter the central Lyman alpha emitter in the aperture, the less number density of faint surrounding Lyman alpha emitters we have in the annulus rings, which makes sense, right? Like if you have higher emissions, like you have a brighter center, you are more likely to have less, you are more likely to suppress star formation in nearby regions. And so, like I said, the stronger the luminosity of the central host, not host, but the central galaxy, the less number density of faint ones we have around it. But the trend isn't the same at higher redshift. This left figure right here is at redshift 5.7. This redshift right here is the second redshift they did analysis on, which is around 6.6. And so you can see that the trend, ignoring the first annuli risk, which is, annulus disk, which is, you can see a clear trend, a good downward trend. So everything, all the Lyman alpha emitters near the aperture have decreased, which makes sense. But the same trend does not apply when you move further out from the central Lyman alpha emitter, which is a bit strange. And so what they did to study this, they say, okay, maybe there is maybe we need to study the surrounding UV radiation field around these central Lyman alpha emitters. And so what they did is, since they didn't have, they estimate the UV radiation, background radiation from the central Lyman alpha around 6.6 redshift, and they came up with this graph, right, this figure right here, which shows the J21, which is the UV radiation field in their study. And so you can see that once again, the stronger the Lyman alpha, the stronger luminosity the central Lyman alpha emitter has, the more, the stronger the UV radiation field around it is. But this trend is not as impactful as it is outside a certain radius. So when you're close to it, of course, you're gonna have more UV radiation. When you're farther away from it, these different colored lines represent the different annulus disks that they used, right? So the farther away you are from the central aperture, the less UV radiation you're gonna have. And so, like, although their UV radiation estimate is within their expectations, they found that that their work is not, their estimates, their analysis is not sufficient enough to explain the decreasing trend in the number of counts of faint Lyman alpha emitters around the central Lyman alpha. And so one of the reasons why could be that maybe their galaxies, or the galaxies measured are too big for this suppression. Yeah, that's pretty much it. Sorry, any questions?
So why the number density is lower around bright gamma emitters?
Why is lower? Well, from my understanding, the theory is that if you have a bright, if you have a bright central Lyman alpha emitter, you're gonna have more UV radiation that is suppressing star formation around its neighbors. And so you can see this trend very clearly in this graph at around 5.7 redshift. The stronger your emission of the stronger luminosity of your central galaxy, the number density of less bright surrounding galaxies you're going to have at any range, right? At any annulus range. That's my understanding.
You understand that? Is everyone okay? That's point D. Who understood why this graph is going down towards greater end? Is that okay? Did you understand or not?
Should I explain?
Who didn't understand? Who understood? I guess you didn't all understand, right? Did you understand?
But these two are different sources, right? Or
I mean, what do?
Which, the graphs or the colors?
on the front.
So the one on the left is observing galaxies at 5.7 redshift, and the graph on the left is observing galaxies at 6.6 redshift. And all they're trying to say is that we have a downward trend at 5.7 redshift, but we do not see that same trend at 6.6 redshift, except if you're really close to your central galaxy. Of course, you're going to have less star formation, but the trend does not appear at further radiuses away from your central galaxy, and they're not sure why.
Right. Okay. So this is teacher. Okay. So this is luminosity, right? So this is teacher. Like me, I have so much pressure, right? Did you understand? Did you understand? So much UV pressure. So no students are around. Okay, this is number nest of students, right? Around teacher it's small. But then this is student, like this. Okay, he has no pressure, right? So the more students are around. Okay, that's the point of this thing. Okay, good. Okay. Okay, thank you, Angel. You have a very good understanding. Good.
Okay, any more questions for Angel? If no, thank you very much, and let's move on to B.
My screen is not sharing. Wait. Okay, so for this afternoon, I will be talking about this paper, the origin of gas in the Magellanic Bridge, meerkat detection of H1 21 centimeter absorption. So basically, the authors in this paper, this is quite a short one because this is just a letter. So the authors in this paper investigate the origin of the neutral atomic hydrogen, or H1, in the Magellanic Bridge using the H1 21 centimeter absorption line. So before discussing further, basically this is the Magellanic Clouds system, and this is the large and the small Magellanic Clouds. So here in the right image, this is just the white veil here is just a representation. So there is a discovery that there is a distribution of gas and dust between these two uh, satellite galaxies. So as we can observe, it is not evident, but there's been observations with the Gaia satellite detected that there is a distribution of stars between the two satellite images. So the authors in the paper want to determine what is the, like, where did the gas and stars in this bridge, as they call the Magellanic Bridge, came from. Is it like from the LMC or the SMC? So in this paper, they presented two competing models explaining the formation of the bridge. So the first model is the close flyby, which proposes that the SMC and the LMC had a close encounter without a direct collision. So this leading to a formation of the bridge through gravitational interaction. And the second model is the direct collision, which proposes that the SMC passed directly through the LMC approximately 100 million years ago, and this resulted in the stripping of gas and the formation of the bridge. So they also explained here the importance of the spin temperature, which basically divides the column density by this quantity, and this is crucial for understanding the physical conditions of the gas and its density. So in this paper, they used a quasar, J0332, as a probe so that they can study the Magellanic Bridge gas. So this quasar is located between the large and the small Magellanic Cloud. So the position of this quasar allows the study of the 21 centimeter absorption line, which provides the critical data for the column density kinematics in the bridge. So what they did here basically in their methods is that they determined the column density by analyzing the absorption line at 21 centimeter and observed this through the Meerkat 64 array last 2021. And they combined this data with the previous observations from the Australia Telescope Compact Array. And here, as mentioned earlier, the quasar was chosen as a target because it is a luminous extragalactic background source, and it provides a strong signal for observing the 21 centimeter absorption line. And here they centered the field of their observation at the quasar. And basically, they the result shows that that studying the quasar revealed a significant detection at the 21 centimeter absorption line. And here in the figure 1, it shows the emission and the absorption spectrum, and the emission is on the top and absorption is on the bottom. And this shows that the absorption features overlaps with the dominant emission peaks, and this result highlights the presence of cold and diffuse H1 gas. And here in the second figure shows the gas to dust ratio of the Magellanic Cloud system, and this illustrates the various locations of the gas to dust ratio along the Magellanic Bridge. And if you can see the contour lines, this indicates the different multiples of the Milky Way's median values. And basically, this figure shows the gradient shows that shows the centers of the large and the small Magellanic Clouds. And basically, there is higher density around the large Magellanic Clouds, and this figure supports the hypothesis of the metallicity gradients and the influence of the large Magellanic Clouds on the bridges gas composition. So let's go back here on this text. So the result shows that as mentioned earlier, the quasar has a higher mean radial velocity than the previous, because previous studies used different probes in observing the dwarf galaxies, or as you can see here, this quasar shows that it has a higher mean radial velocity, and that the analysis showed earlier in figure 1 showed two prominent peaks on the H1 emission line, suggesting that there's complex gas dynamics. And then the findings basically they were able to derive the column density in the area, and their findings support the direct collision scenario between the SMC and the LMC. So they concluded here in the last part that their methods and their results supports the model B, which is the collision scenario. So their result shows that the similarity between the bridge gas to dust ratio and that of the LMC shows that the components of the bridge originated in the LMC rather than that of the SMC, since the gas to dust ratio of the SMC is far higher. So this implies that the bridge was extracted from the LMC. So basically, this paper is a support to the second model, direct collision scenario of the SMC and the LMC. I think that's all for this paper. Any questions?
So can I ask a question?
Yeah.
There are two velocities, right? Where does that correspond?
Here in figure 1.
Here, the LMC and SMC, or where is it in the group?
I think this is towards the quasar, and I think they just tried to check with spectroscopy, like the emission at around 21 centimeter line.
Yeah, so you see two velocities, right?
Yeah.
So what are these?
I think, they mentioned this also, like here, that the presence of two prominent velocity components in the H1 emission. I think they mentioned that it is not unique, but a common feature throughout the whole MCS. I'm not sure what particularly like the velocities describe, like the emission lines, but they mentioned that it is not unique, but it is common throughout the cloud system.
So there are two gas clouds with different velocities.
I think that is it. Yeah.
Okay. Okay, fine. And then I didn't get it, but then why they prefer what is the
Model T.
oh
Yeah, because the results shows that the gas to dust ratio agrees more with the large Magellanic Cloud rather than the small cloud.
okay? Do they show that? Where do they show that? Is that in a video?
Here, I think in their calculation rate. I'm not sure if I highlighted it. Wait. Oh wait, there's a table here. Oh, here. I'm not sure if where I'm not sure where is the quantity that they were able to mention the LMC is but they mentioned here that there are similarity between the gas to mass ratio of between the bridge and the large Magellanic Clouds.
Okay. I see. Okay. Thank you very much.
Thank you.
Any other questions, comments? And do you understand why there's an emission and then also together in video?
Not really.
I think based on my understanding here, this shows that there is a presence of cold and diffuse gas, meaning I can wait. Something to do with the velocity, I guess. I'm not sure. That's also like I haven't looked into like why is cold and diffuse gas important as a tracer in this scenario. I'm not sure yet.
So, quick question: when it's coming, the bottom axis is velocity.
The absorption.
Oh.
Absorption. The meerkat.
Okay.
Meerkat data.
But it's showing positive and negative values. So I'm just confused. Like, is it blue shifted and red shifted? So depending on one or the other, we have absorption and emission, or am I mixing that up?
I think that these are separate observations.
Oh, okay.
And they tried to see the profile to determine the velocity profile, the velocity of the components. If I understand it correctly. So yeah, they were able to derive the velocity resolution for through the emission.
So top one is emission, bottom one is absorption.
Yeah. And they are, I think, different data.
Okay.
So why did they use the quasar?
Because they also in the previous studies they used quasars as probes because they needed something brighter to detect the 21 centimeter line, as I understand it. Yeah, because previous studies use these objects. I think they are also quasars.
So I'm not confident, but I think the absorption is on the quasar spectrum, I think. And emission is just directly observed gas. If you look at the quasar is so bright, right? So if the quasar's light goes through the cloud, it has absorption on the quasar spectrum. But then if you observe the diffuse gas, you just see the emission, I think. That's what I thought, but then I'm not 100% sure. So
Isn't it like these observations are towards like the emission and the absorption is towards the quasar?
but then it's weird, right? Why one observes emission, another observe. Can you check that in a paper, then maybe comment it on Facebook?
Okay.
Okay, thank you. Very interesting results.
Okay, so I think it's time to move on to Dora.
Anyone hear me?
Yes.
I'm Dora. Today I'm to present the paper is about measuring the Hubble constant using localized and non-localized phase radio bursts. And Hubble constant is one of the standard lambda CDM model, but there's a gap than 4 sigma, which is given by two main ways. So they use 108 localized FRBs and 526 non-localized FRBs to constrain Hubble constant again. So there's early time probes is given by CEMB, cosmic microwave background. The value of Hubble constant is 67, and the late time probe is given by Cepheids supernova 1A sample. The value of Hubble constant is 73. So between these two ways, there's a gap more than 4 sigma called Hubble tension. So they take FRBs as an independent way to measure Hubble constant. And because FRBs are produced outside the Milky Way, so there's a characteristic quantity, dm. It is integral of electron number density, so it's not possible to distinguish the partition between dm IGN and dm host. Okay. So use electricity energy simulation to calculate the dm IGN under different redshift value. This section is under constraint on Hubble constant with localized FRBs. So the red dot is localized FRBs, and the blue line is from TNG 300 simulation. So then use MCMC to obtain value from the posterior distribution, then just to ensure the number of samples are enough to estimate Hubble constant and the uncertainty. So this black dashed line is Hubble constant value 69, and this 2 dashed line is also include 1 sigma confidence, and the green and orange region is the previous work from supernova 1A type and CMB model, and also in 1 sigma confidence intervals. Then move on to constraint with non-localized FRBs. So this figure shows the pseudo redshift under different DM value from H-galaxy, and the red dot is pseudo redshift of each non-localized FRBs, and we will take this value to measure Hubble constant. And the blue dot and blue yellow arrow bar is the result of MCMC. Use this red dot to run MCMC, then we can get this result. And the black dashed line is also represent the Hubble constant 68, and also in 1 sigma confidence. So, but because of two kind of errors, one is statistical errors, and because we calculate the DM value on these like this kind of formula, so there's statistical errors like omega m, and it is about let me see. Okay. And omega m is about 1.8% error, and so they use MCMC to estimate Hubble constant. The Hubble constant is 69. So it is similar to what we did from localized FRBs and non-localized FRBs. So maybe that means statistical errors doesn't influence Hubble constant too much. So that's the second error is systematic errors. And like FIGN, the fraction of baryon density, the uncertainty of FIGN is about 8%. So to calculate the Hubble constant in more precisely way, it may using independent way to constrain FIGN, then to reduce the systematic errors from Hubble constant. So for future work, so they get Hubble constant value equal to 69 from 108 localized FRBs and 68 from non-localized FRBs, and then statistical, if including lambda m to calculate Hubble constant again, it will get 69. So for future work, as the number of localized FRB increase to 500, the uncertainty of Hubble constant will be reduced to 1%. But because there are many non-localized FRBs, much more than localized FRBs, so it still can use this to measure like for non-localized FRBs to measuring Hubble constant again.
Very good summary. Any questions, comments? Did you understand how people can estimate Hubble constant using FRP?
Basically, they plot the DM whose versus CM.
Why that does what? Okay.
Because the DM whose have relations to the H4 in so the DMX crude is DMIGM plus 1 plus DM whose divided by 1 plus Z. And the DMIGM we can find in equation 3, right? So there is a H0. So there is a direct relations with the DM whose and HO.
Oh, okay. I guess I'm asking why there's a direct relation physically.
Because the universe is expanding and they are.
Yeah, you're getting there. And then?
And when the signals coming from the FRP and they go to a certain medium, and they will affect by the HO also.
How? Why does it affect HO? Okay. Can you explain better?
Which one?
Why you can measure the Hubble constant using dispersion measure and redshift? How does it work?
For localized FRPs, we get the DM value and redshift already. But for non-localized FRPs, we didn't get a value accuracy. So because the non-localized FRP are far from us and is extragalactic, so it will have so many electrons or something between us. So to calculate these, we can, there's a formula. To calculate the density, we can get a distance because of the integral formula. I can find the formula. This. So we can find a distance, and then we can plot the DM value and redshift on the same figure, I think.
Good, excellent. Yeah. Is that okay? So to measure the Hubble constant is measuring the expansion speed of the universe, right? Then you need two of them, redshift and distance. Redshift is sort of speed or velocity of the expansion of the universe, right? And then we need to know where is that space. We need to know the distance. And then this is kind of difficult. For redshift, we can measure it easily if we know the host galaxies. We can take spectra, we know the redshift. But the distance is always difficult in astronomy, right? And then here, they're using dispersion measure. As Dora explained, if the light troubles more are coming from the more distant place, then it's dispersed more through that equation, because it goes through the neutral ionized electron more, and then get more dispersed. So in principle, in a short way, if it's more dispersed, it's more distant. If it's less dispersed, it's nearby. That's why you can measure the distance. Then you compare distance and redshift, and that gives you the expansion speed. Okay, so that's why measuring the distance it's always important in astronomy. Any other questions, comments? Any question from NTHU? Okay, if not, Dr. Gary.
Thank you all.
Thank you, Laura, and let's decide who will present the paper tomorrow. So currently, Saim Malima already registered, so we need 2 more volunteers. Huh? I'm sorry.
Who is registered?
Saim Malima.
I can do that tomorrow if you want.
Thank you.
Am I going to be here tomorrow? Yes. Yeah, I can do that tomorrow.
So anyone else in Wednesday team?
Okay, so
How about Tomoki?
Okay. I will do.
You? So tomorrow we have Shine Malima, Tomo-san, and Tomoki. So thank you everyone for joining today, and see you tomorrow. Bye bye.
Thank you.
Thank you.